disappear and then you won't hear anything.
Okay.
So I will.
Okay, it's preparing to go live. Done. Okay, go ahead.
Can you share?
Yeah, I can start.
Okay, welcome back. Okay, so I was showing.
Just wait a couple of minutes to see if everyone connects. Just in case.
Sure, I will wait for your signal to start.
Okay, so we have 33 persons watching. We had 170, so let's just wait a bit. $50, so it's going up again. $58. $63. Okay, people are starting to connect again slowly. 67. I don't know. Maybe we should start so that this will not be too much delay on this. Okay.
Okay.
Go ahead.
So I think this is pretty close to where we left off before the short break. And this shows global monthly temperature anomalies. And the last time the Earth had a below normal month was December 1984. Gave my first talk on climate change for my boss in 1985. I was on the fence. I didn't think that us puny humans could affect something as vast as our climate system. After doing some reading, a year or two later, I was convinced we were, and the evidence is quite convincing that we are changing our planet. So, and this is the way I look at fire. Other people have slightly different views, but I see three drivers, three ingredients, and whether you're in Australia or the Amazon or the Arctic or in Spain or Portugal, you need all three of these for a fire to occur. Fuel, what type, how much, how dry it is, all important aspects of fuel. Ignition, humans and lightning. Weather, hot, dry, windy, extreme conditions. So as I said, you can live with dry and windy as well. Some people, separate fuel out to fuel amount and fuel presence, that kind of activity. Some people add humans to this list explicitly. Some people add climate separately from weather. It doesn't really matter how you slice and dice, but you need these ingredients. And, for a long time, I was a weather person, and believing that weather was the key one. I've now, and I'd argue with fuel people all the time, but really fuel moisture is the nexus of fuel and weather. And because fuel moisture determines if a fire will start, whether it will spread, how much fuel is available to burn, which means how intense that fire will be, which means how difficult to impossible it is to extinguish that fire. So fuel moisture drives the fire business. So I'm going to show some recent work that's not published yet, and it's based on our Canadian Fire Weather Index system. And I know some of you are quite familiar with it, and some of you may not be. It's part of the Canadian Forest Fire Danger Rating System, and the FWI system is a weather-based system. We do have more fire behavior prediction system that uses fuels and topography, but I'm just going to talk about the FWI system. And simply, there's four meteorological inputs: temperature, relative humidity, wind, and precipitation. And there's three different layers of fuels and the most moisture codes, moisture contents associated with that. and then we have some intermediate indexes, initial spread index, and buildup index, and the fire weather index. Unfortunately, they named the system, and one of the components of the system have the same name. So there's FWI system, and there's a fire weather index. So this is based on dead fuel moistures, and there's time lags for things like grass for like less than 2/3 of a day, to heavier fuels like peat or down logs on the forest floor. They're closer to 52 days. That initial spread index, it represents how fast a fire might spread. Fire weather index indicates how intense that fire may be. The buildup index indicates how much fuel might be consumed. And both ISI and FWI have been used to define an active spread day. In Canada, we often use FWI 19 as an active spread day. We also use ISI of about 9 as an active spread day, but that can vary regionally and around the world. FWI system is unitless, it's qualitative. It does not include fuel types. So if you want to know how fast a fire is spreading in meters per minute, or how intense that fire in kilowatts per meter fire line, you need that fuel information. So we took ERA5 data, and it's the 5th generation from the European Center for Medium Range. And 1979 to 2020, there is new data from ERA5 back to 1950, and we are looking at that. But we used this data and calculated FWI components for the entire globe. And we used our package to do this, and we did use an overwintering function. Places like Canada, much of the country gets snow in winter, so there's no fire danger, and there's routines for calculating the startup conditions in spring. So we looked at trends, and we use standard techniques for determining the trends, and we're only going to show a number of maps. I'm only going to show the significant trends in some of the input variables, as well as some of the FWI components that are related to intensity, rate of spread, etc. We use a biome classification system from FAO and WWF, World Wildlife Federation, and we calculate fire season length. This is a bit coarse, and we hope to refine this. Right now, the minimum number of months where 90% of the area burned happened at that location. And there's some examples there, and I got Europe there with unfortunate Oceania table there. That was my mistake. I was supposed to put the European table there. The European table is here, but it's a little hard to see. The reds, are often summer, but you can see there are fire seasons in spring and fall, and even some in the winter in the Northern Hemisphere. So let's look at the trends. And some of these are not going to be surprising. These are mean temperature trends. And, like I was showing, we have been warming, so this isn't a surprise. This is 1979 to present day. So this isn't looking at the future. This is what has happened, okay? So is this warming already having an impact in the FWI system? And we'll get there. Daily precipitation trend. Not much, a little drier in parts of Africa, but really nothing significant going on. Mean RH, some places are getting drier. The red areas are getting drier in terms of relative humidity. The blue areas are getting more moisture in terms of relative humidity. And I saw some recent work from India. I was wondering about, is this real? RH is going up, and there's a lot more irrigation going on in parts of India that suggests this is the reason why we're seeing increasing relative humidity there. Mean wind, a little bit here and there, a bit windier in Africa and the Amazon. Maybe deforestation is playing a role there. So now we start looking at the 95th percentiles with the premise that extremes drive the fire business. So we want to look at the extreme end. Vapor pressure deficit is an indication. It kind of combines temperature and RH into one variable. How effective is the atmosphere drying those fuels? And as you recall, I said fuel moisture is the key here. And you see California, Europe, Africa, it's fairly significant in areas where we have been seeing more fire. Not so much in the boreal yet, but I think that will come. There are some parts of the boreal, but right now, the Amazon and Europe, Africa, southwestern United States, parts of Mexico, increasing significantly. ISI, so how fast a fire may spread. South Africa starts to show up really strong here, southeast Australia, but many increases, not very many decreases. India showing up as a decrease, but these are how fast fires may spread. And FWI trend, 95th percentile, and you see the trends, southwestern United States, Iberian Peninsula, yeah, it's showing up, South Africa and Africa, South America. So these are trends that are showing up. Now, this is an animation, and hopefully you can see this. This is global temperature anomalies. Blues are colder than normal, the baseline being 51 to 80, and reds, oranges, yellows, warmer than normal. And you can see this, the years are shown. It's kind of like a 5-year running mean in the bottom center there. And we're a much warmer planet than we used to be, and seems to start around the late 70s when things really start to warm up. So there are models of the future, GCMs. When I started, they were general circulation models. Now most people call them global climate models, but the acronym's the same, and suggest significant warming to 2100 and beyond. If we look at the models that go to 2300, it gets really crazy. Hopefully we get our act together as a global community and do something about it. Greatest increases over winter, spring, over land, though the Arctic Ocean will probably become seasonally ice-free. Some people say 2030s, some people say 2050s. This is going to change the climate system in northern latitudes significantly. Projected increases in extremes. Once again, this is really significant to fire. If there's more heat waves and more droughts, we will see more fire. There'll also be more rain and flooding on the flip side. And this is consistent with climate change. And we'll talk about jet streams in a little bit. Okay? There's a lot of variability in time and space. Now here's another animation of what the future may look like. And there's lots of models around. I use the Canadian model, I'm Canadian, but yeah, I could use the European model, the UK model. There's Australia, there's 20 some models. But and you can see hopefully you can see the time change in the top there. And this is towards the end of the 21st century. And it's much warmer world, if we continue on this path. And this is RCP 8.5, which is the more pessimistic or business as usual, but the path we're on right now is pretty close to this. And you can see in the bottom legend temperature scale, 10 to 15 degrees. I mean, that is just crazy. So I've done a number of studies in climate change, and one of the things we find for boreal and mid-latitude systems is the role temperature's playing in fire activity. And here I'm not talking about individual fire. I'm talking about fire over a larger area, like California, say, or Portugal or Spain, over a period of a month or a fire season. And so why is temperature so important? Well, 3 reasons. Fire people love 3s, if you haven't already noticed. Fire seasons are getting longer. And where I'm from, Alberta, officially our fire season used to start April 1st. It now starts March 1st because our fire seasons are starting earlier, ending later, but so far it's been starting earlier. Warmer gets more lightning. Most of our increase, our area burned in Canada has doubled since the 70s. And it's all due to lightning-caused fires. And a longer fire season means more opportunity for lightning, but a warmer atmosphere also means more opportunity for lightning. So more lightning, more fire. But the third reason, and probably the most important, as the temperature increases, that vapor pressure deficit increases, the atmosphere gets much more efficient at sucking moisture out of the fuel, unless there's increases in precipitation to compensate for this warming. But the models don't see that happening, thus fuels will be drier. Drier fuels means it's easier for fire to start, easier for fire to spread, and means more fuels available to burn, which can lead to higher intensity fires that are difficult, challenging, impossible sometimes to extinguish. This is work done by the US National Academy Climate Change Report a couple of years ago. And this is looking at change in precipitation. And you can see for summer, for places on the west coast of North America, spreading inland, it is going to be drier. Okay, so if it's warmer and drier, this is kind of like the worst combination you can imagine. And speaking of worst combinations you can imagine, the incredible, unprecedented fire activity in Australia. I think it was 17 million hectares burned. Look at 2019, the hottest and driest year on record. This is New South Wales. The number I quoted in terms of area burned was for all of Australia, not just for New South Wales, but it was a record year in New South Wales for obvious reasons. So I'm just going to do, this is some older work, but it's global. So I thought I'd put in here, and looking once again at the Canadian Forest Fire Danger Rating System, which you either are familiar with or now have a little inkling of it from a few slides I shared with you earlier. But we use something called DSR, and it's the daily severity rating, and it's derived from the FWI, which represents intensity. But someone wanted to get an idea of how much effort it was to put out a fire. So it's more related to a perimeter of a growing fire. So it's FWI almost to the exponent 2, almost squared. And we look at cumulative because fire seasons are getting longer. So we want to see that cumulative load of how difficult it is to put out a fire in the future, according to these Gcms, these global climate models. And we looked at fire season length, and we used 3 different models, and a lot of these suggested, areas of 3 to 20 days longer and over 20 days. And this is for mid-century, and this is using an old carbon pathway. And this was using the Hadley model, this particular one I'm showing. And then if you go to the end of the century, there's a lot more longer fire season. The stippled area already are running at year-round fire season. But here's looking at the cumulative DSR, and hopefully you can see the animations and large increase, a tripling of cumulative daily severity rating. The orange is 1.1 to 3 times. Yellow is almost not much change. Blues, I don't see many blues. Might be a few. I don't see any blues anymore. Would be decreases. So the fire severity, according to this FWI system index, is going to increase significantly. Now, the thing about extremes is escape fires. So if it escapes, that's when you have a problem. And so if you look at the distribution, and if our distributions are changing, and whether they're input variables to the FWI system like winds, or the actual FWI components themselves like fuel moisture, if we're shifting to more extremes, then something that used to be, in this example, a probability of 1 in 60, shifting our distribution could now mean the probability is 105. And, are we reaching a tipping point, a breaking point, where we're going to see more area burned? And I have colleagues who've done studies and suggest that, exceeding thresholds in terms of escape fires could see area burned increase by 8 to 11 times. And what did I say about California earlier? A factor of 8 increase since the 70s, which is incredible. So jet streams. So I talked about extremes, and this jet stream, of course, we all know what jet stream is, but we're not flying anymore. It's that band of fast air. If you're flying with it, you get to your destination earlier. Flying against it, you're delayed. But this really dictates our day-to-day weather, and it drives everything. And it gets its energy from the temperature difference from the equator and the northern hemisphere, the difference with the Arctic region. the Arctic region is warming up much more rapidly than the equatorial areas, so that temperature difference is getting smaller. So instead of a fast flowing river, it's becoming like a lazy river with eddies and whirlpools. And this is important to weather because if you have a fast flowing river, the highs and lows go through every 3 to 5 days. And if you get rain every 3 to 5 days, you're not going to have a fire problem, okay? But with these eddies, you get stagnation and you get what we call blocking ridges. And blocking ridges have been known to the fire people for 60 years as being conducive to weather, to fire conditions, fire activity. And it's kind of like the opposite of your grade 3 water cycle. Air sinks, warms, and dries, okay? And if it stays stationary, you get drought and fire. Conversely, where the lows and troughs are, if they're stationary, it's your grade 3 water cycle. Air rises, cools, condenses, forms clouds, and rains. But if it's not moving, it keeps on raining at the same location, and you get flooding. And that's exactly what we're seeing. So we're seeing this stagnation. Now, this is still an area of research, and some people aren't convinced. We're actually starting a study to see if blocking is becoming more frequent with the warming. But this is something of concern. And there are a number of papers out there, Michael Mann's one example, stating that we are seeing more extreme weather. So we use something called spread day events. I mentioned earlier ISI, FWI, but we can also use satellite data to determine how active a fire is spreading. And we don't use size of fire, but we use growth, linear growth. And if fire advances 2 meters per minute for at least 4 hours of burning period, that's 480 meters on a single day, we call that an active spread day. And so using definitions like this, we can see how active things were. And of course, we can use the ISI and FWI, and that's what's done in this panel on the right. And I didn't put the citation. This is by Wang et al. And looking at Canada and spread days, what was observed and what may happen in the future. And we're seeing significant days where significant fire spread can occur. I hope to do work like this globally for this fire risk project that just got funded, and it's a great opportunity to look at fire spread opportunities, which really drive the fire business. It's these extreme days. So, I am getting close to the end of my time. I'm almost close to the end of my talk. We'll have a couple minutes for questions if you have some. What can we do about this? And for us, we can update the Canadian Forest Fire Endangering System. Parts are 40, 50 years old, need updating. There's more demands on it. Early warning systems, machine learning. If you have large volumes of data, machine learning is an excellent tool to look at severe fire weather, extreme fire weather episodes, to give that 3 or 4 day warning so you can move resources, focus on community zones, and we're doing that. We have programs like Fire Smart, FireWise in the States. I'm guessing there's something similar in Europe. Fuel management, harvesting, grazing, carbon management. Of course, we have to look at everything from emergency management phases, prevention and mitigation. Some people combine them, some people separate them. Preparedness, response, recovery. Some people include review. Every community needs emergency management plans. So there's lots we are doing, there's lots we still need to do. So fire and weather are strongly linked. Changes in forest fires may be the greatest early impact on climate change on forests. Longer fire seasons, this be a problem for fire management because we're seeing high intensity fires occur outside the traditional historical fire season. More fire occurrences, more crown fires, fires that spread from the surface up to the crowns of the trees. These are high intensity fires, difficult to stop. Increased fuel consumption, more area burned, more carbon emissions, more activity in the future. Our fire management has to adapt to this new reality. I don't like the term new normal because there's nothing normal, it's a new reality. We're not on a plateau, we're on a trajectory for more and more fire. Entering new territory, no analog. So we can't just rely on our experience, the unknown unknowns. We have enough trouble with the known unknowns. Fire and society interactions, unfortunately, will continue to increase in the future. We have to learn to live with fire and smoke. Fire is a multifaceted problem and will need multi-pronged solutions. And I do thank you for your attention. here's a slide, and we're on Twitter, Instagram, and there's a website. That's a Pyro CV from Northwest Territories 2014. And there's a podcast there, World on Fire, if you're interested. And I think I'll stop here. And there's time for a few questions. I'll do my best to answer them. And do you want me to stop sharing my screen, or?
Okay, Mike, you can leave that slide if you want. Thank you very much for your very interesting talk. I apologize for this mishap that we had in the middle. I hope it did not disturb you and the audience about following your excellent presentation. You showed us a very, let's say, not very brilliant future. Let's say what we can expect due to climate change is not very good, I'd say. So the questions are, what can we do to try to cope with these changes that we are seeing will be global, and particularly in some regions of the world will be more intense. And I understand there was a question also from the audience about asking what you mean by more sensors, or by more remote sensing. What is what you mean by that?
Okay, so the first question, a little bit more what we can do. All human-caused fires are preventable, and some regions of the world are doing a good job. And through education, right from school kids, early age education is important, using tools like fire bans, and at times we use something called forest closures, and I'm sure other jurisdictions in the world as well. When you get those extreme days, you shut down the forest. That means no tourists, no hikers, canoeists, no industrial operations either. And it's only a few days of the year. And, one of the provinces that I used to live in, Ontario, they have agreement with the forest industry that on those extreme days, they'll take the day off. It's just too dangerous to be working in the forest. Power lines, they can be buried. Many of the California problems, the 2018 California fires, the total cost of those to society was over $120 billion. You can bury power lines. You can harden the system. There are things that could have been done. So preventing those, making our communities more resilient, and that's a whole talk in itself. And I mentioned FireSmart, FireWise. You can go online and check those out. And there's lots of principles, guidelines to make homes and communities more fire resilient. We can't make communities fireproof, but we can reduce the risk of catastrophic fire. The other question was about remote sensing. I'm talking about satellites, and Emilio is much better qualified than I am to talk about this topic, but there's multiple sensors, different wavelengths. Some of them are very sensitive to fires, like the 3.9 micron channel band, and so they can detect heat signatures from fires. There's also burn scars, because green vegetation can turn to black, and you can detect that in many different channels. So area burned globally is determined by remote sensing, number of satellites up in space, taking pictures all the time on various wavelengths that they analyze and use. And there's a number of global databases. GFED is one example, but there's many more. And GFED, Global Fire Emissions Database, I'm guessing the acronym. I just use it all the time as the acronym. Guido van der Werf is one of the key players behind that, but there's many other databases with key players behind them. Emilio can set the record straight when he gets to chat. So that's what I meant by remote sensing. And the numbers change from year to year because fire changes from year to year, but sensors have changed, including small fires has made it more precise than it was in the past, more accurate as well. But there's challenges, smoke and cloud. Some fires are understory fires, so the canopy kind of is still alive and can block, any kind of probing to try and determine that burned area. So there are a number of challenges with using remote sensing from satellites to determine global area burn. If that was the question. If not, I'm sorry.
Okay, Mike, I have still a couple of questions here for you. And before we give the floor to Emilio, let me put them, if you can also care to think about, to say something about them. What are your thoughts on fire perimeter simulation programs such as Prometheus? And the other one is, to what extent do available climate models differ in their projections of FWI? I think that this means that there are different projections, different scenarios, and what is the variability that you find there? So these are two questions. I have another two before we close.
Okay, I'll try and be shorter so I don't sneak too much into Emilio's time. So fire growth models, excellent tools, okay? Firesight, Prometheus, there's numerous examples of them, and they're getting more sophisticated and better, and some are now starting to use machine learning techniques. A very effective tool, fire management uses them and will continue to use them, and they're good for operational, but also good for research purposes. And so, yes, some of them are fairly complex and takes a while to learn how to use them, but they're an excellent tool. Scenarios, yes, there's a lot of variability, and you know, they're not perfect. Okay, these are models. Okay, they're very sophisticated models, and they've done a fairly decent job thus far, and they're still working on ENSO cycle. They quite haven't captured that perfectly yet, but each iteration gets better and better. But projection of the future, yeah, it's who knows what the future will be for sure. But we are getting warmer, and these are different pathways of how quickly we get warmer, and eventually, hopefully, we'll stop warming. But it depends in large part how we as a global society deal with greenhouse gases and land use changes, not just greenhouse gases, but greenhouse gases are the biggest part of our warming at this time.
Okay, let me put you a couple of questions more. We saw relatively less fire activity this year in Canada. There may be less human activities due to COVID-19. But the question is, are there other weather climate factors that could be considered the cause of this as well? And to finish, last question, how do you feel about the balance between prevention and suppression? Should we allow remote fires to run their course by burning without human interference? I think you would address already partially this topic, but if you want to consider it again.
So Canada was really quiet this year, and there's a lot of year-to-year variability. And area burn is a complex variable because fire management plays a role, how many fires occur at the same time, the weather, of course, plays a role, the fuels in terms of area burned. If it was recently burned, it's unlikely to reburn unless it's grass. So there's lots of reasons why there's variability from year to year. In Canada, even though our year was warmer than normal, our summer was cooler than normal. So we were cool. So it's where the ridges were and where the troughs are kind of dictate what happened. And there was a blocking ridge over Siberia and one over Western United States, but nothing over arboreal. So we had a very quiet year. Next year could be crazy. So you kind of have to look at a running average or a moving average and over a longer period of time, because I didn't show the year-to-year burning in Canada, but it's like up and down, up and down, and up and down. It's kind of like the temperatures, but there's a general trend up. Okay? So, yeah. Prevention and suppression, yes. Studies have shown that for every dollar you spend on prevention, you save $4 to $11, depending on the type of activity and where you are. So yeah, ounce of prevention is worth a pound of cure is an old saying. It's true. Okay. So fire management agencies around the world, it varies a great deal, but a lot of them spend most of their money on large fires and on suppression activities. Preparedness is important, initial attacks important, but we spend way too much money fighting these large fires. And if you can prevent them when they're small, or prevent them by educating the public, which reduces that they even occur, then we're much farther ahead. So absolutely, prevention and mitigation, we need even more emphasis on.
Thank you very much, Mike. So we close here now your part, and I thank you again in the name of all. It's a pity that we cannot see all the almost 200 people that are following this presentation. And without further delay, I'll give the floor to Emilio and invite him to talk to us about this problem of risk of fires. Emilio, please.
Okay, thank you. Thank you, Domingos, and your team for organizing this. It's always a pleasure to work with you, and hopefully with a new project we can come back to things that we worked together in the past. So basically, I'm trying to give you some thoughts on fire risk concepts and how most of the critical variables that should be considered in fire risk could be derived from different geospatial technologies. And then I will move to provide some ideas on how these different components of fire risk could be somehow integrated. Well, first, I should remind you what we mean by risk. In the wildfire terminology, we have been using sometimes different concepts to other natural hazards, but the most common ones differentiate between two components in risk. One would be danger, meaning the probability of something, some sort of natural hazard to occur, both in space and time. And that obviously is related to the physical conditions of a particular area. An area that has a high risk of, or high danger, sorry, of being flooded, for instance, will be obviously much more prepared than a society where this event occurs very unlikely. So societies typically prepare, obviously depending on their technical development and economical means, but societies are typically prepared for what is likely to occur. I don't know if you are familiar, but we have a very heavy snow in Madrid 2 weeks ago. There was the heaviest snow in 50 years. And obviously, some people thought that why this is completely blocking the city, since this type of events occur in New York or in Chicago or in Toronto very often. Yes, that's the point. They occur there very often, not here. That way we are completely blocked. The city was completely blocked as a result of that, because we cannot be prepared for something that occurs once every 50 years. It's impossible to have the means to tackle these issues. So obviously, these type of events have a strong impacts. That means that you cannot do a lot of things in the city, but you can always do something new in the city, like for instance, skiing or do ice skating or something like that. So typically, societies are prepared for things that occur likely, that are probable to occur. Then there is the second step, the second phase, let's say, of risk, which is vulnerability. That's exactly what we are meaning by preparation, how the society is prepared to deal with that particular hazard. In that aspect, that is sometimes not, I would say that it has not been widely considered in fire risk, as I will mention later. Within this vulnerability, typically we consider the exposure aspect, meaning what population or what type of human activities will be affected by this natural hazard, and vulnerability, which would be more what is the level of, let's say, of preparation or resilience of that society. And risk should be the product of these two aspects. So meaning that We don't have risk if there is no danger. If we are very far from a volcano, we are not prepared for a volcano eruption, of course. No? So there is no danger, no risk. But it could be a high danger, but a high preparation, therefore a low vulnerability, and therefore also low risk. So in many natural hazards like flooding or volcano eruptions or earthquakes, we cannot do much on danger, but we can always do something about vulnerabilities to improve the preparation. I think Mike was actually talking about this issue in preparation for the future conditions of fires as a result of climate and societal changes. In any case, I think it's worth to remind that risk is a human concept. So we only have risk when there are humans potentially affected by that natural hazard. No? If earthquake occurs in an area that is completely inhabited, then we don't consider that as a natural hazard. So we are actually basically focusing on the human impacts of any of these events. What are the phases of fire risk, of risk management? Basically, first, we need to assess the risk conditions, where, when this event can occur. Then risk mitigation would be mostly affecting the emergency situation, and how can we really reduce as much as possible the impacts of that event. And then restoration and adaptation, which means after the event occurs, after the fire occurs, what can we do, let's say, to recuperate as quick as possible, the values that we lost. So going to fire risk assessment systems, which is the first phase, I think that is the backbone of fire preparation. And then I think we need first to define which are the critical variables, what's affecting the danger and the vulnerability. Then we should develop methods to generate those variables, considering the spatial and temporal requirements, then integrate those into synthetic indices, validation and reassessment of them, then communication, how can we communicate that? Mike was also talking before about the importance of education, or to reduce or to increase, let's say, the vulnerability, to reduce the vulnerability of societies. Then we need to mitigate risk and then be adapted to future conditions. I'm going basically to talk about the first aspect, that is the main aspects within the fire risk assessment system. Well, all of us know that fire is a complex issue that relates to different factors, including mainly two groups: fire ignition on one hand and fire propagation on the other. We need to consider, of course, weather conditions, but also topography that affects propagation, and also the amount of moisture on fuels. We need to consider fuel types and conditions, and we need to consider human and lighting aspects, which at the end are the main cause of fires. Obviously, if we are referring to fire risk assessment and reducing fire risk, is because we consider that fire has negative impacts, but we also should consider that fire has positive impacts, particularly in dealing with some natural processes in several ecosystems that are well adapted to fire, and they need really fire to keep, let's say, in good health conditions. But also we have negative impacts of fires in terms of atmospheric pollution. This is something that we probably have not put much attention in the past, but I think we should definitely, because it is quite an important aspect of fire impacts in terms of socioeconomic damages. We also obviously need to take into account the casualties and house burns, ecosystem services, reduced or lost as a result of fire, and ecological damages. Obviously, all these negative impacts very much depend on the conditions of the fire. What are how much intense or how much severe are those fires, what is the residence time of the fire on vegetation, what are the characteristics of the area affected in terms of resistance or resilience of vegetation, even the society preparation to them, and also the soil and climate conditions. So when defining a fire risk system, we need first to consider what are the users of that, and there should maybe very different users depending on first their level of decision. We have international bodies like FAO, the European Commission. We have obviously the management level at the country, and the country different institution in terms of civil protection, environmental ministry, or even military emergency services. We have regions, we have local authorities, and these different users should provide different requirements. No, the risk products are not necessarily useful for everyone. It depends very much on what are the use. So we need to adapt, let's say, our system to what will be the final end users, and try ideally to develop systems that are flexible enough to cope with many different type of users. Well, there are several risk assessment systems in place for quite a long already. You are familiar with, well, the most well-known are the US, the Canadian, Australia, and some European nations, of course. And as you see, most of the components of this system, this one, for instance, the last version of the national US fire danger rating system, they are mostly focused on weather conditions. I mean, wind speed, relative humidity, temperature, vapor pressure deficit, etc., rainfall, of course. In the system, there is the system contemplates the idea of including other aspects, like, for instance, the causes of fires, particularly the human dimension of fire. And that is part of they call human cause fire occurring this, but actually it's not used. No, it's very it is not really in place, and that somehow occurs also in the Canadian system. Mike was mentioning before the well-known fire weather index. That is obviously a weather an indicator of the weather conditions at different temporal scales. But the whole fire danger rating system of Canada includes also other modules. The fire behavior prediction system is already in place, is already developed, but you see here that we have the fire occurrence prediction system that should be an integration of lighting and human cause, but it's not yet fully developed. The official websites of Canada says that is under consideration. So the FE system in Europe also is pretty much a weather-oriented fire risk system. So that means that really we are not considering one of the main factors actually that causes fires. No, Mike was saying before that 95% of the fires are human caused, and therefore we don't understand human aspects. We are missing an important aspect of the fire risk assessment. In my view, the current fire risk assessment systems has some limitations. Obviously, they have some strengths as well, but they have some limitations. No? Weather modeling is fine, typically, because that's the main focus of these systems, but sometimes it's too coarse. For instance, the FIT system provides data at 8-kilometer resolution. Sometimes it's too short, so it provides forecast data for one day or a few hours, but not seasonal forecasting. That may be quite useful also for strategic planning. Then another important limitation is that most of the system, as I have said, they are focused on weather, but they don't consider other aspects like live fuels, for instance. What is the moisture content of live fuels? There is very little or none consideration of human aspects, and there is almost non-consideration of fire vulnerability. You know, what are the resources at stake? What are the ecological and societal potential impacts of fire? Then obviously we need to include the new fire risk assessment system, all these aspects. We need to include better information tools that provide accurate and update information from all these variables. We also need to improve the communication services, particularly not just linking to fire emergency system, obviously, but also to the ordinary citizens that are at the end the most affected by fires. Then we also need to improve governance and strategic planning, particularly in the area of prevention, because sometimes the measures are either unavailable or they are not really reinforced, particularly evacuation plans, for instance. So that's why we try with this new project that will start in a few months to provide a more strategic vision of fire risk, including both aspects, danger and vulnerability on one hand, but also these different phases of fire risk: assessment, reduction, and adaptation to future conditions. And also, on top of that, let's say fire risk is not an isolated risk. Sometimes occurs connected to other risks, like, for instance, windstorms or flooding, etc. So this also should be connected somehow with the risk evaluation. Well, the second part of my thought, of my talk, would provide some ideas on how these different variables that are relevant for fire risk assessment could be combined. I'm going mostly to mention some of the methods that we use in a project that we run for a national system that could be somehow applicable at different spatial scales. So first, causes. The causes of fires obviously are basically natural and human aspect. The natural factors, the most current ones, obviously, lighting. Lighting, globally speaking, is probably about 5 to 10% of total fires. In some areas is more important. But the problem with lighting is that most of the fires occurred by lighting, they tend to be more intense than others, because in many cases this lighting occurs in dry storms, and many strikes occur simultaneously, and they are very difficult to handle. In terms of human aspect, we have intentional fires, fires that are set up intentionally, let's say, purposely for pasture management, or as a result of social conflicts or land use transformation, particularly in tropical regions for deforestation, or mining also in tropical regions. But also we have plenty of fires caused by negligence or accidents that may be related to agricultural burning, landscape, or recreational activities, or hunting, or power lines, or railroads that may cause, again, important fires. How can we model these fires? Well, basically, we have two choices. One would be more empirical modeling, in which we have, let's say, historical occurrence of fires, and we derive a database of potential variables explaining this fire occurrence, and then we apply different empirical fittings. It could be a statistical regression analysis, or it could be some sort of machine learning approach, like in random forests or support vector machines, or deep neural networks, etc. The other approach is more deductive. In this regard, we are basically exploring what are the actual relations between human ignitions and different factors. And we try to model those factors and then apply those relations, let's say, to a larger territory. This has been the approach followed by the use of fire models within the dynamic global vegetation models. This is an example of that by a paper a few years ago, in which they model the human risk as a result of human density, population density, as you see these this function is not linear. So in other words, you have more files whenever you have more people until a certain peak in which you start having less files because we have more dense population and therefore you will have more means to extinction. In terms of fuels, I think you know that moisture content is a very important variable in terms, particularly for detecting extreme conditions. Not just dead fuels, but also live fuels are quite important. Dead fuels basically are estimating dead fuel moisture content by using different weather indices. Most of that comes from meteorological station of weather forecast, but also we can do something with meteorological satellites. We actually estimated a few years ago with Meteosat and the equivalent moisture content. In terms of live fuels, obviously you can do field work, but this is quite demanding, quite an effort, and sometimes not very representative from a spatial point of view. Therefore, remote sensing is quite a valuable tool. In this regard, you can do empirical fitting between your moisture measurements taken simultaneously with the satellite acquisitions, and then provide some sort of empirical fitting between them, or you can either use simulation models based on radiative transfer equations in which you simulate different scenarios, then analyze which one of these scenarios is close to your reflectance measurements, and then you inverse the model to estimate moisture content. In both cases, you can get fairly good results. This is something that we derive in a national park in the center of Spain using AVHRR data. But nowadays with MODIS, with another satellites that are now available, we can generate a much wider view of moisture content conditions. In terms of fuel types, there is a great variety of fuel type descriptions available for different fire danger rating systems. Basically, we can map those fuel types using fieldwork, again, very demanding in terms of effort and spatial comprehensiveness. We can use ecological gradients in which we estimate the potential productivity of vegetation, and therefore we can associate to different fuel conditions. And also we can use remote sensing data, both including indirect classification using previous products like land cover or vegetation, but also with a direct classification using optical sensors or using active sensor like LiDAR or radar data. This is one of the products that we generated in the past. And this one is derived from a reclassification of different remote sensing derived products, but mostly land cover on one hand, and the percentage of tree cover. Also, we use LiDAR measurements at global scale, and also the ozone biomes were used for this classification of fuel types using the fuel class classification system. Direct mapping of fuels can be done with optical sensors. In the case of the traditional optical sensor, they are limited because particularly for the vertical description of the fuels, but still they can provide fairly good results for the discrimination of some of the fuel types generally used. But if we use radar or even more LiDAR, the quality of the estimation is much higher because we can analyze the vertical structure of the fuels. And you can see the R-square values for estimating these variables that are quite difficult to estimate even by fieldwork are really quite impressive. So you can get very, very good correlations, and therefore you can estimate, I don't know, foliar biomass, crown volume, tree height, crown bulb density, and some other variables that could provide a quantitative assessment of fire propagation. The biomass is well established in the literature. This is something that also we did in the past for Mediterranean vegetation. You can even mix the LiDAR data with other optical sensors. This is what we plan to do actually in the project that we just going to start. In terms of vulnerability, this is something that really has been very unusually covered by risk assessment systems, but I think it's quite important to realize what are the potential impacts of fire and also be more prioritize, let's say, the actions to protect different values. There are obviously human components of vulnerability, which are related to the protection of people that are working in fire extinction, but also lay people in areas affected by fires. The case of recent European catastrophes has been quite important in this regard. Obviously, we always have the issue with the wildland-urban interface, which is one of the most risky areas in terms of fire protection, and also we have the issues with infrastructures. In terms of ecosystem services, these are also societal values, but they are, let's say, indirect affecting the people. I mean, ecosystem services are quite important, of course, as well. Wood, pastures, mushrooms, recreational, soil erosion, carbon stocks are among some of them. All these ecosystem services can be approached by economic functions. You know, there is already a long tradition of environmental economics to value ecosystem services to society using different approaches. In the case of fire impacts, we can value the potential impact of fires, but by analyzing what will be the reduction of value from after the fire to before the fire, so what has been lost as a result of fire. But also in the case of some ecosystem services, these services will not be available for quite a long period after the fire. I'm thinking, for instance, in wood production. So therefore, we should add to the value lost, the integration of these losses throughout the life or the recovery life, let's say. And that is the typical formula used by economics to compute composed interest. And this value, the log n, means the years in which these ecosystem services will not be available. We estimate a certain discount rate. So one of the critical conditions there is how do you estimate n value to integrate the losses throughout the life, let's say, of this absence of that particular ecosystem service. And obviously some services will be recuperated fairly quick, like grass or shrubs, but obviously for some others, it will take much longer. So we analyze different strategies for vegetation that would obviously affect the recovery time, but also the soil conditions and the vegetation, the precipitation conditions for those particular years. And you can come out at the end with an economic assessment of the potential values that will be affected by fire. This is controversial, of course, because you can always discuss about the approaches, but at least there is something to be this. I mean, it's a good framework to start discussing about the importance of prevention and extinction. Well, we also have the ecological values that should be also part of vulnerability, and this is even more difficult to value in terms of putting, just say, euros per hectare or something like that, because some values they don't have economic values, they have other values, I mean, other non-economic values, let's say, but to some extent also that should be part of the vulnerability. And then we can consider the specific conditions of the different landscapes. Obviously, the protection figures also should be important there, and also the role of the different landscapes in the whole landscape pattern, let's say. The integration of these different components, danger and vulnerability, can be done with different approaches. First, we need to somehow get to a common scale for measuring danger or measuring risk. We can use probabilistic models, we can use euros per hectare, we can normalize variables. At the end of the day, if we need to integrate information coming from different sources, such variety of sources as we have just mentioned, for instance, an economic value is euros per hectare, but if we want to mix mix with moisture content, which is in proportion of dry weight, then you need to you need to find out a common scale, not to integrate them both. Once you have this common scale, then you need to find out models that help the integration of these different variables, and we can use physical models or artificial intelligence approaches, and then we need to somehow assess the product of this integration. Some examples of that, for instance, physical models related to fire propagation equations. We can integrate different variables, including obviously weather conditions, topography, fuel types, etc. And we can provide, let's say, a spatial assessment of potential areas affected by fires. Or even we can drop on the space random ignition points and then analyze the integration of the potential probability for anywhere in the space. So that could be also an important, interesting approach to analyze the potentials of anywhere to be affected by fires. Another physical approach is the fuel class classification system that we use for one of the dissertations, the PhD dissertations done in my department in the last years. And in this case, the fuel types were used to define fuel beds, and the fuel beds were fed by different meteorological variables using the ECMWF forecast data, the ERA interim, if I remember well. And then we, from this variable, the different components of the fuel class classification system were derived to obtain an estimation of rate of spray, flame length, and reaction intensity. And we derived this at global scale. Obviously, we realized that this product has a limited interest for local analysis, but at least it can give you a global idea of what are the trends. And we are connected in this regard with EFIS, the European Forest Fire Information System, that is now responsible for generating a global one-line information system. So this type of data could be helpful for that. In terms of integrating information using artificial intelligence approach, and we have some experience with random forest, which is a well-known algorithm for classifying and extracting, let's say, the relevant variables for classification analysis. These models can help to can provide a fairly good fitting between observed and predicted variables. In this case, we are modeling the burn area variability worldwide, and these are the sensitivity analysis that provide an estimation of which are the most relevant aspects for explaining, in this case, the burn area variability, which in this case it was the Human Development Index was a quite important aspect there, the actual evapotranspiration, the maximum temperature, etc. And at the end, you can provide a spatial assessment of these different variables that I think is quite useful to better understand what are the driven factors behind in this case, burn area variability, for different ecosystems. This is a paper that is not yet published, but I hope it will in the next few months. In terms of communication, first there is something. This is not trivial discussion of whether the fire risk conditions should be communicated, because I remember conversation with some end users in one of the national projects, and they were concerned about this risk assessment system because they consider that if we inform to people when and where the fire is more likely to occur, people who are setting up intentional fires, they will have a guidance, let's say, to be more harmful. Well, this is something that we should consider, but obviously, in principle, we assume that the better we inform the people, the safer it would be for everyone. And the mean to do that will be either using emails, using web mapping services, or using different mobile applications. There are plenty of technical means nowadays to inform people, including ordinary citizens. Just as a summary of what I try to present today, I think fire risk should be an integration of many aspects, not just weather conditions. I think weather conditions are very important. Of course, if everything is fully wet, it will not burn. Even if everyone is trying to burn, it will not burn, of course. So we need fuels dry enough to be burned, but you can have very dry fuels and not having a fire at all. So it's not just weather conditions, it should be something else. We should include all relevant factors, and of course we should mitigate fires considering all relevant factors. We cannot do much in modifying weather conditions. We should do more in modifying climate conditions if we really take in seriously the climate mitigation policies. But that is obviously long term. But we can do much more in terms of other aspects, like managing fuels, like educating people, reducing vulnerability, increasing resilience of societies, etc. So to me, a sound fire risk system requires good models, requires accurate information, and this is something that I am particularly interested in because most of my background is trying to generate critical variables for wildfire risk conditions and post-fire impacts, but also we need solid governance, while keeping in mind that the risk is always there. It's always there. We cannot avoid completely fire risk or any other, having fire risk in areas that are likely to be fired, to be burned. And I like this idea of Einstein. The ship is always safe at the shore, but that is not what it's built for. So if our societies are somehow related to fire, we will have fire. The point is, how prepared are we for fires and how resilient are we for fires? In other words, how can we reduce the negative impacts of fires? Thank you.
Thank you very much, Emilio, for this excellent lecture. And you opened lots of ideas, and you brought different challenges to us. As you mentioned, this is very, very broadly the backbone of our European project. We are going to work around these ideas and to develop them, and hopefully to try to apply them first at the European scale and eventually also more global scale as well. There are some questions already coming from the audience, but if I can take this situation that I have and put you two questions as well. You showed something that is based on the past situations, let's say on the statistics, on the probabilistic tendencies of the different parameters. But we have now to face a new situation that is changing. And as Mike pointed out, let's say we have to face the days with much warmer conditions, much more extreme conditions. And how do you think we can give this step from using the past to predict the future in this situation of change?
Well, yeah, as I tried to say, I think we should identify those factors that are where we can act, let's say, We cannot reduce, we can reduce danger to some extent, of course, but we cannot avoid completely danger of fire, because at the end of the day, fires may occur. No? What we can, I think, we should focus more in trying to reduce vulnerability, and that means putting more effort probably in education. No? Well, coming back to the example of the last 2 weeks in Madrid, the people didn't know how to act because they were not accustomed to snow at all. So we didn't have really a good equipment, no, to deal with such a heavy snowstorm. But obviously the people of Toronto, the people of I don't know, New York, they are very well prepared because they know what to do. No? If an earthquake happens in Japan, everybody knows what to do. The point is that if a fire occurs in a region where fire occurs, why the people is not prepared to act, no? To evacuate, no? So that is something I think that we need to reflect now. And also in terms of education, in terms of particularly reducing emissions coming from accidents or negligences, or intentional fires, of course. So there are, I think, plenty of room, no, for trying to improve the human aspect of fires. No? While obviously we need to better understand other factors like fuels, like weather, of course, but the human aspect, I think, also is quite important to reduce the.
Okay. Let me bring you 2 or 3 questions of the audience. The first one is, how can we address different temporal scales on fire risk assessment? And then how to connect seasonal, monthly, weekly, daily, and even hourly scales on the system? This is one question, and if you want to consider the second one, small patches that escape from fire, so fire refugia within the fire perimeter, can be crucial for post-fire recovery. Is there a way to identify these small refugia by remote sensing?
Okay, well, the integration of temporal scales, I think we need to define systems that are flexible enough to incorporate different sources of information. Obviously, if the forecast data is quite important, is quite relevant, but also the actual data, weather station on the ground that are not really, most of them are not really accessible in real time. So I think we need to also improve the long-term forecast, seasonal forecast. There are groups working on that. And there has been some papers published that relate, for instance, the variation of ocean temperature in fire occurrence. Obviously, this is related to El Niño, but not only that, in other occasions as well. So I think we need to develop a wide range of strategies for that. But in principle, the actual integration of temporal scales should be much easier than the spatial scales, because it will be a matter of applying to the same territories, and therefore it will, probably the most critical challenge is how to download properly the weather data to the local levels of detail that we need. In terms of small fires, let's say, and this is an important aspect, of course, any remote sensing method is able to detect fires that are a certain size, depending on the spatial resolution of the system. Global products that are being used, for instance, for burn area mapping, like the ones that Mike was showing before, they rely on systems that have a 500-meter resolution, spatial resolution. That means that small fires are going to be missed. And actually, we tested that comparing a global product in Africa with a product that we generate from Sentinel-2 data that is 20-meter resolution. So comparing 20-meter with 500-meter resolution came with a very different view of burn area, because 90% of fires smaller than 100 hectares were completely missed in these global products. And in tropical regions, that is an important aspect. It's almost 50% of the whole area is burned in small fires. So if you miss them, in case of the detection, active fire detection has been mostly based on coarse resolution sensors, like 1 kilometer or something like that. You can detect obviously much smaller fires than 1 kilometer because the thermal contrast is quite high. So you can detect, let's say, fires of 50 or even 100 meters with a satellite at 1 square kilometer resolution. So what really means in this case is to go into a very high thermal sensitivity for doing that. At this point, we don't have dedicated satellites to estimate very small active fires. I think the launch of the 3rd generation Meteosat could be a step ahead, because that system would provide 1 kilometer detections every 10 minutes. And 1 kilometer detection every 10 minutes, that means that probably we can go as small as 20 square meters to detect the fires. And that would be even better than the actual ground systems. But the system is not yet launched, and we hope that could be done in the future. At this point, you should rely on UAVs, I mean drones or something like that for detecting small patches.
Emilio, there are other two or three questions. Early warning systems are very important, but next step is to provide near real-time risk assessment and local nowcasting of weather conditions. What is your opinion on this? And another one is, should human health, both physical and mental, be considered part of risk assessment?
Well, the first part, yes, I think the early warning provides, let's say, is mostly addressing, let's say, fire managers for planning decisions, no, of how to inform people and how to organize their resources. But yes, real time, I think, is quite important as well. You know? So we need systems that would provide real time information, particularly in the emergency situation. Yes, human health. Yeah, I think definitely we should improve the current evaluation of fire impacts by considering these aspects that has not been much done in the past. Mike was saying before that around 300,000 people may die as a result of fires, but the vast majority of that number is because of the pollution derived from fires. And we really haven't done much research on that. So that's something that we really need to reinforce in the future, yes.
Okay. There is a final question I hear, but I think you already answered it previously about the reliability of geospatial data to detect and characterize fire locations. But in the first question, there was one point that you did not address exactly, because what was asked was if we can identify islands in the middle of burned areas that can be useful for post-fire recovery and also for ecology.
Yeah. Well, if you work with medium to high resolution satellites, yes, you can of course detect patches within burned area that are not affected by fire. I think Sentinel-2 is great for that point of view. It's free data. You can download it for free. It's 20-meter resolution. Actually, several bands are at 10-meter resolution, and it's every 5 days. So it's really great for doing that. We are already analyzing Sentinel-2 in Africa, which is one of the most difficult areas to map fires because the tropical climate reduces a lot the signal, the post-fire signal. So you need really a lot of high temporal resolution to map burn areas there. And this, yes, you can really detect very small patches. So yeah, detecting islands is definitely feasible with remote sensing. Yeah.
Just one last question popped up. I think it's very much related to what you were just saying. The question is directly, is Sentinel 5P data a potential source for fire risk monitoring? What's your opinion?
Well, for Sentinel 5P is mostly an atmospheric satellite. And that means that the system can provide you an estimation of emissions, some CO2, CO, I think N2O as well. So yeah, for detecting emissions, it could be a good source of data. For fire risk, as I have considered a very comprehensive list of variables, no, it will be just providing data mostly on actual fire or post-fire conditions. I mean, the detections of particles and gases derived from fires, but not really the preparedness of fire risk, let's say.
Okay. Thank you very much, Emilio. May I ask, Mike, do you want to make some comment or put some question to Emilio as well? Or both of you? Okay.
Thanks, Emilio. I look forward to working with you. Risk is a challenging topic and has many definitions, and I think your approach is logical and something that needs to be done. And I enjoyed your talk. I enjoyed the pictures of snow at the beginning. It reminds me of home. So no, I thought it was an excellent presentation, and I look forward to seeing you again in person, hopefully next year.
Yes, hopefully. Yeah, we are missing travels these days.
Yes, among other things.
Among other things, yes.
Okay, so thank you very much to both of you once again for participating in this seminar. And I thank all the attendees also for their attention to what has been said. And there was a lot of participation, as you could see. We had lots of questions. I had to filter some of them. And at this stage, I would also like to thank my staff for the support for the preparation of this event, particularly to Luis Mario for his technical skills and his ability. And to our students and to all our audience, we say goodbye now. We wish you to stay safe and take care, and hope to see you face to face soon.